Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as we do every night during Advent of Code, we're going to be working through the new puzzles in C++. I want to thank you for watching. If you're watching on Twitch or you're watching the replay later on YouTube, you can always go to the channel description on Twitch. There you will find links to the YouTube channel with the stream replays and the GitHub repo where we upload all of the code that we write. If, on the other hand, you're watching on YouTube, just check the video description right down there. You're going to find a link to the Twitch channel with the live streams, and once again to that GitHub repo where we put all of the code that we write. So we have just about a minute and 15 seconds to go until tonight's puzzle drop unlocks. Day 19. We're getting into the home stretch here. Puzzles are getting a little more difficult, a little more tricky. So far, we haven't been fully stumped on any of them. We've definitely gone down some garden paths and had to do a little bit of debugging. But you never know. Tonight might be the night where we run into something really hard, have to take a step back and think about it some more. But we will see. So I have already set up the little skeleton of a solution program here for day 19. It is, like we have every night, just a simple main program that does nothing but return 0. But I've already included my check and IO libraries that we use to do assertions, and we use to read files in the puzzle input, because we use those pretty much every night. And I've set up this build file in the Bazel build system. It just tells Bazel how to build this program, what the source code is, what its dependencies are. And over here in the terminal, I've already, given it a run once, and it doesn't do anything because it's just an empty skeleton program so far. So we have just a few seconds until tonight's puzzle unlocks. All right, day 19. As your probe drifted down through the area, it released an assortment of beacons and scanners in the water. It's difficult to navigate the pitch-black open waters. If you can build a map of the trench using data from the scanners, you should be able to safely reach the bottom. Okay. Beacons and scanners float motionless in the water. They're designed to maintain the same position for long periods of time. Each scanner is capable of detecting all beacons in a large cube centered on the scanner. Beacons that are at most 1,000 units away from the scanner on each of 3 axes. Okay, it's 3-dimensional. X, Y, and Z have their precise location determined relative to the scanner. However, scanners cannot detect other scanners. Summaries automatically summarize the relative positions of beacons detected by each scanner. Okay. For example, if a scanner is at XYZ coordinates 500, 0, minus 500, and there are beacons at the listed coordinates here, scanner should report the first beacon, but it would not detect the second beacon at all. Unfortunately, while each scanner can report the positions of all detected beacons relative to itself, scanners do not know their own position. You need to determine the position of the beacons and scanners yourself. Okay. The scanners and beacons map a single contiguous 3D region. This region can be reconstructed by finding pairs of scanners that have overlapping detection regions such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely determine where the scanners are relative to each other. Okay. For a moment, consider only 2 dimensions. Suppose you have the following reports. Drawing X increasing rightward, Y increasing upward, scanners as S and beacons as B. Scanner 0 detects this. So we have this. Scanner 1 detects this. For this example, assume scanners only need 3 overlapping beacons, and the beacons visible to both scanners overlap to produce the following complete map. Unfortunately, there's a second problem. The scanners also don't know their rotation or facing direction. Okay, so we're getting into kind of a complicated geometry problem here. Due to magnetic alignment, each scanner has rotated some integer number of 90-degree turns around all of the X, Y, and Z axes. As one scanner might call a direction positive X, while another might call that direction negative Y. The 2 scanners might agree on which direction is positive X, but one scanner might be upside down from the perspective of the other. In total, each scanner could be in any of 24 different orientations, facing positive or negative X, Y, or Z, and considering any of 4 directions up from that facing. Whew, boy. Okay. Here's an arrangement of beacons as seen from a scanner in the same position, but different orientations. By finding pairs of scanners that both see at least 12 of the same beacons, you can assemble the entire map. For example, consider a following report. Okay. So you have a set of scanners here, a set of each of them has coordinates of beacons. Because all coordinates are relative in this example, all absolute positions will be expressed relative to scanner 0, using the orientation of scanner 0 as if, okay. Because the scanner 1 must be... Ooh, boy. This is a tricky... This is kind of a complicated one. Full list of beacons relative to scanner 1. Told there are 79 beacons. Assemble the full map of beacons. How many beacons are out there? Oh my goodness. Well, let's start to figure this out. We'll get our puzzle input. Day19.txt. And we already have the beginnings of an n-dimensional geometry library in this dimension grid, but we are going to need to extend it in some ways. So, okay. Let's take a look at what that input looks like. Day19.txt. Okay, we've got 37 scanners, and all of them have lots of stuff. Okay. So, looking at dimension grid here. So this dimension grid thing is something that I've already started writing that can represent points and vectors and stuff in any number of dimensions. So we can think about this that sensors are points and vectors are the position relative to the points of beacons, and we can start looking for overlapping sets of beacons. But what we need to be able to do is figure out some rotations of these things. And, oh boy. We need to figure out how many beacons there are total in the first step. So, I mean, I guess the initial thing that we can do is we can look at the first scanner's beacons, and we consider the first scanner as being the origin, and we use the first scanner's orientation. So anything that's visible from the first scanner, we can just do head on this. So any set of coordinates that's visible from the first scanner, we'll say we know those are already beacons. But then we have to see if we can find something that is anchored. Oh boy. So the region can be reconstructed by finding pairs of scanners that have overlapping detection regions such that there are at least 12 beacons that both scanners can detect within the overlap. Okay. Each scanner could be in any of 24 different orientations. So facing positive or negative x, y, or z. I'm just still trying to read this carefully. So we're looking at 24 each scanner could be in any 24 different orientations facing positive or negative x, y, or z, and considering any of 4 directions up from that facing. So I think, okay. So facing positive or negative x, y, or z, there are 6 possible facings. Like, it can be like pointed at one of 6 different axes, and then the up orthogonal to that can be any of the 4 perpendicular axes to that. So I think we need to be able to rotate vectors 90 degrees around certain axes. So let's try and write something that does that. So the axis that we rotate about will stay the same, and there will be 3 possible axes when we rotate. Okay, yeah, I'm going to switch over to my code view here. So we've got these vectors represented by this vec class, and I want to figure out how to rotate them about different axes. So we'll say we're rotating about a certain axis. So if we rotate about the x-axis, the x value is going to stay the same and y and z change, et cetera, et cetera. And then we'll say int turns, that can be 0 to 3, but basically turns is see, I'm not sure how this actually works in 4 dimensions. So we are going to go ahead and put a check in here that dim equals 3 for this rotate 90. Because although I wrote this to be generic in any number of dimensions, I can only really conceptualize this in 3 dimensions right now. I am not a higher dimensional being, so we'll go ahead and just write this for 3 dimensions. So let me think here. So if we've got 3 dimensions, and let's say that z is the fixed one, and we have I might actually want to sketch this out a little bit to sketch how these rotations work, but basically well, you can watch me kind of try and do this just in ASCII art for myself. But if we had, say, x equals 1 and y equals 2, then we'd have a point right up there, and we rotate it 90 degrees, and we wind up with x equals 2 and y equals -1. And then if we were to put this out a couple more, doing ASCII art just like Advent of Code, 180 degrees, we'd wind up with something right there, and then yeah. So first of all, we'll take turns and say that we will do it modulo 4, and then we'll say so we've got this deltas array here, and if about axis is 0, then the first axis will be 1. The first coordinate that we are actually changing will be 1, otherwise it will be 0. And then for the second one, if the about axis is 1, then the second one should be 2, otherwise it should be 1? No, no. If the about axis is 0, then the second one would be 2. About x. I'm sorry. Let me just figure this out here. So just going through the possible about axes here, 0, 1, and 2 for 3 dimensions. If it's 0, then we would have 1 and 2 here. If it's 1, we would have 0 and 2. And if it's 2, we would have 0 and 1. Okay, that is correct. So we've got our first dimension and our second dimension. And now, oh, I'm sorry, I should actually show you the code, of course, while I'm writing this, while I'm starting to write this. So we've got our first dimension and our second dimension, and what we need to do is the for int t equals 0, t is less than turns, about that axis, plus plus t, then I think we'll have to save one thing as a temporary. We'll say, well, that equals the first dimension, and then we will say first dimension equals the value of the second dimension, and the second dimension equals minus the value of that was originally held by the first dimension, that temporary value. And actually, this is modifying it inline, but what we really want to do is return something new. So we'll say vec rotated. Start by copying this, and then we'll do rotated dot deltas to get those references to the first and second dimension that we are rotating about. And so yes, I think that is all correct. And then we return rotated. Okay, so we've got something that can rotate a vector by 90 degrees about any axis, any number of turns. So there are 3 axes, up to 4 turns. It's going to give 12. So I think facing is the one other thing. Oh, man. Now I think we're still okay here. So don't know that we necessarily need any more in dimension grid, so let's go back to our actual solution program here and get it started. So obviously we want to include util/dimension grid here. And let's try and, well, so let's get a struct to represent sensor data. And within this, we can have a vector of our vex of and we should be able to mutate those, you know, each of the 24 different ways that that it could be. So just looking through some of these examples. Well, let's start parsing so that we have some data to work with, to look at here. So so there are blank lines in between the scanner data, so we'll say vector of strings which we will read using our read lines from file routine. And then we will split that up into a vector of strings just splitting by new lines, or split by empty strings in the lines. And then yeah, for each of those, so we'll say for we're going to build up a vector of this sensor data. And we will skip the first line because that's just the numbering the scanner. So we'll go ahead and use an iterator. Equals scanner desk dot begin +1, skipping that first line. go all the way to the end. And then in there, for each of these lines, have a vector of string views of we will get that by stir, splitting the line, stir split in there, yes. So we will use stir split on that line value, split it by commas. We'll make sure that there are 3 parts there. And then we will say, we will actually parse into a vector here. Dimension grid 3 vec. Relative, and we will use simple A to I for each of the positions in that vector. In fact, we can just make it a loop for d equals 0, d is less than 3, plus d. That's an integer. We'll do that as an integer. We will check. So simple A to I, parsing one of those strings into one of the deltas in those relative numbers. So this should give us all the sensor data parsed. I am going to go ahead and add the proper dependencies here, and we'll just make sure that we can parse to begin with. And we are getting into the tricky days for sure, but I think that, we'll take this step by step, and I think we'll get to a solution here. We might not be the absolute fastest, but we're going to get there. And we also need that dimension grid library of ours for n-dimensional geometry. I am realizing that it would be a little bit simpler if I just had like a grid 3, like a 3D grid library instead of this n-dimensional, but who knows, maybe part 2 is going to ask us to do this in 4 dimensions, so, let's go ahead and try and just run this on the input, and it shouldn't actually do anything. I just want it to, at least make sure it doesn't crash. Okay, so it's done something. I think, do we have I/O for this stuff? Do we do anything with streams already? Did I already write? Yes, I did. Okay, so we can actually check that this parses okay. So I'm just gonna, on the very first one that we parsed, I'm gonna just spit it out. So we'll just say actually, I want that to be... Oh, we didn't actually even put this in the signal, did we? So what we should be doing here is... each one of these that we process, then sensor data dot and place back, move that relative vector. Just sensor beacon signals, and then we will do okay. So we go through all the beacon signals there, and we will just spit out the vector there. The vector there. not working for you? Standard O stream and Vec. I don't want stuff in O stream. Okay. Couldn't infer template argument dim. Okay. This should work. 259 should work. Man, that was gonna be so nice for me, but that can't possibly be a thing that's okay. Yeah, I was gonna say, no. Okay, darn. Yeah, just a sec. Wonder if I can fix this up if instead of having this be out of line here, I make it an inline friend of the vet class, and then maybe it won't complain about trying to overload that. We'll see. We do not need that. We will say friend. We will declare that inline friend. Just const vec and v, and we'll see how that treats us. It's no longer complaining, so let's give that a whirl. Okay, and I'm just going to open up our original input here. 774 at the bottom it is what, 576 640 521. Yeah, that all looks like it parsed okay. And since we just did that for fixing the output operator for vec, we'll go ahead and fix that for point and hyperplane as well. And finally do it for hyperplane. I think we're going to actually use hyperplane for reflections too. So we'll use all the fun stuff. Okie dokie. Okay, so we can get all of our sensor data read in as vectors here. So next thing that we need to do is figure out all of the way that those vectors would look like in all of the 24 possible orientations. So we can have facing x plus or minus x, y, or z, and then 4 ideas of what up is relative to that. So I think, and we will maybe use some of the example data to test this, but 2, 3, I think there's 5 there. We can, well, yeah, let's say we'll have a method here that returns a vector of sensor data that gives all possible orientations. So for each of the 3 dimensions, we can reflect over the plane at that dimension equals 0, and that will give us the facing directions, and then there will be 4 rotations there. So I'll say 4 dimension equals 0 through 3. Reflect in false and true, whether we reflect over that, and then 4 turns is 0 through 3. So it's going to be 3 times 2 times 4 is 24. That should give us the 24 different orientations. So now let's see, to actually get this, what dimension grid, we have reflect point P. Yep. Okay. Yeah, actually, I don't think we're going to be reflecting across a hyperplane, because that I've only implemented for points, but I actually think that for vectors that just means that, you know, we'll flip a dimension or not. So basically, standard vector sensor data, all orientations, and then we will have this orientation. So you will say if reflect Actually, we'll copy this initially, and we'll just modify it in place. So we'll just say, if we are reflecting, then for for each signal and beacon signals, we are going to flip the value at that dimension. Oh, that's got to be this orientation, obviously. We're not trying to modify this one. This orientation dot beacon signals. We're working on the copy. That's so we should be good there. So if reflect, we do that, and then we also rotate. So I'm trying to think, if we reflect across a given axis, is that the same, or given, oh man. So if say that x is the dimension that we've reversed, so we're facing positive or negative x, then we would want to rotate about the x-axis. Changing y and z would change the facing. So I think, yeah, I think that all checks out. So actually, I'll just modify these all together now that I think about it. So we'll just say, just do one loop. So we'll say, if reflect then we do the minus, and then oh no, that we actually just want to say signal then equals signal dot rotate 90 about the axis divided by that dimension, and then that number of turns. So, and then you'll put that on the list of all possible orientations. Okay. And then finally down here we will return all orientations. Okay, so I think that this gives us the different kinds of rotations, but to kind of check that out, I am going to take one of the like sample toy inputs from the website that it shows us for different rotations, and I'm going to go ahead and test out with that. So that's one example, and we can look at and see if we get some of the same rotated orientations if we do that. So instead of just printing out this stuff, what we're going to do is say for sorry, not auto, const sensor data. So for a particular orientation, we will go ahead and spit that out. So we'll just say, in much the same format as it gives us on the website, just because that's going to make it very easy to see if we get it right or wrong. Well, not going to be exactly the same, but we'll do print out that signal, and then we'll do a new line there. And this will give us far more orientations than they actually give us in the example, but we should be able to see if we're kind of on the right track here. So I'm going to go ahead and run this with the test input now. Okay. So we got a lot of different things here. We've got our initial one, -1, -1, -1, -2, yeah, so we've got everything that we initially expected. Let's see if there's one that goes 1, -1, 1, 2, -2, 2, 3, -3, 3, 2. Oh, is that a... Question is that a bug, or is that just a different one? Let's try and find another one that starts 1, -1, 1. 1, negative, okay, that's 1, -3, okay. Two, -2, 2, 3, -3, 3, 3, no? Uh-oh, we might have gotten this wrong, maybe? I mean, obviously we got the first one. And then for the second one I'm looking at here, we're looking for, this in the second one. So, sorry, let me move that over there so you can actually see it. So starts with 1, -1, 1, 2, -2, 2, 3, -3, 3, 2, -1, 3. So this is different in some dimension, but let's try and find another that does. So 1, -1, 1, 2, -2, 2, 3, -3, 3, and that does not match that next one. That's okay. 1, -1, 1, 2, -2, 2, 3, -3, 3, and then that doesn't match. Okay. So it seems like we are not necessarily doing all the arrangements correctly, at least according to the example that we have on the website. So I actually feel kind of okay about the rotations, but maybe we are wrong on the reflections. Or just the x being positive or negative, or maybe we need to... I don't know. So, just for now, I'm going to take out all the reflection stuff. And do just rotations and make sure that what we see with just rotations, that, well, hopefully we find valid stuff with... Oh, you know what, though? You know, never mind, actually, because it doesn't... Yeah. I realize now that, you know, we are... Well, no. No, everything that we see on the website we should actually be seeing, so... So we are doing something wrong here. You just look at the rotate method again here. Yeah, I'm pretty sure that's all good. Yeah, I need to ponder this a little bit here, just to make sure that we get all these rotations right. So maybe the way I'm doing reflections is wrong. Or maybe I should do the reflection after the rotation? I mean, I wonder. No, that shouldn't make any difference, actually. Or should it? I mean, just to see what happens, I'll flip the order of those. I don't think that's actually going to make any difference, though. I think reflection might be the wrong way to look at it, but we'll see what we can get to. So we're looking for, once again, this pattern. Oops. You want 1, -1, 1, 2, -2, 2, 3, -3, 3. And then, no, so not for that. Not for that. And then that's not right either. Yeah, you're not seeing that anywhere. What about negative everything here? And then there should be one that is -1, -3, -2. So there's another one, I'll show you another one that I'm trying to look for here. Okay, so we got that one. -1, -1, -1, -2, -2, -2, -3, -3, -3, -1, -3, -2, 465, -708. So we found that dang one. Okay, let's look at another. 1, 1, -1. 1, 1, -1. 2, 2, -2. 3, 3, -3. Okay, not that. I'm beginning to think that, like, this kind of feels just like permutations. Because, well, okay, so if you have 3 numbers, there are 6 ways to put them in any order. And then, well, for each of the 3, you'd have a total of 8. That wouldn't quite work, but yeah. Not just any permutation, because you'd have twice as much then, but yeah, I don't think that's changing anything. Yeah, I think that's correct for the rotation. Let's double check. Think about this again for the first and the second dimension here, maybe. So if it's 0, this will be 1, and this will be 2. Ooh. 0 means this is 1. This will be false, so this will be 2. Okay. 1 means this is false, so this is 0. This is false, so this is 2. 2 means this is false, so this is 0. And this is true, so this is 1. Okay, that should... Dimension selection, should work as we expected. Need to make sure of that too. Yeah, okay. Didn't fail us there. We are producing 24 orientations, but some of them are maybe wrong. It'd be really nice if the examples they gave us on the website included all 24 different orientations, but no such luck. And so far, 82 people have gotten a gold star on this, so the answers are starting to trickle in. The fast people who knew their geometry well are already starting to solve this. We'll see where we get here. So I'm really trying to think. So just purely as an experiment, if this reflection, maybe reflection, we change the other two things? No, I don't like that. Let's just print out all the ways that it does this, so we'll just say just to and that does all look correct for at least the way it's applying this. So this first one, we're rotating about the x-axis, so should be flipped and negative. Flip and negative. Flip and negative. Yeah, so the rotation looks okay. 1, 2, 3, 4 rotations. Now this one, we would be flipping in the x direction. I'm thinking about it though that it's really like reflecting over a plane. Yeah, reflecting over a plane, you'd still only change one dimension. Purely experimentally, I'm going to just try changing the non-dimensional. Just say, I mean, this is trial and error at this point. This doesn't really match my geometric intuition, but we will see. Let's see what this gives us. So let's go ahead and look for some of our special friends here. So we'll look for 1, -1, 1. The first one. 1, -1 done. 2, -2, 2. 3, -3, 3. Got that. 3, -3, 3. Nope, not that. 2, -2, 2. Not that one. Not that one. Not that one. Okay, so that that nonsense didn't improve the situation any. Actually, let's maybe just start to think about like reverse engineering some of this stuff. So going from so we know this is our initial version, right? And so the magnitude of everything in the first, okay, in x is inverted. And then, okay, magnitude of everything in the x dimension, everything in the x dimension is the negative of itself. So we could say that that is, you know, consistent with reflecting in x. These others here, these are the same, these are the same, but then here, these last three all look like they are rotated. Or flipped in some way. I wish they told us the steps that I took to get here. So this other one, you know, the first three, it looks like, you know, negative, negative, except that the way that our operations are constructed right now, one dimension can either stay the same or be negated, and the other two participate in rotation. If I've got that right here. Oh boy. Yeah, you're actually seeing some stumping on the stream right now as I try to figure out the geometry here. We'll get there eventually, but it might not be pretty, folks. Honestly, looking at one of these where things are really distinct is probably going to be more valuable to us. So the magnitudes stay the same. And to get to the second one, you know, it's like a rotation. So it definitely seems like, well, actually let me get all of the examples in here, and just, we can use this to confirm some of our intuitions. So we say 1 2 3 4 5. Yeah, there's 5 there. Okay. So just looking at some of the example coordinates here. Here the x magnitudes are the same, they're just negated from going from this one to this one. Here, x magnitudes are not necessarily the same, but 3360, 1, 2, 2, 3, 3, 6. So here, y is the same, except, yeah, actually, -1, -2, -3, -3, -6, 0. Okay, so here, y is the same, and there's maybe some funny rotational business with x and z. Here, 3, 3, -6, 0. Here, y is negated, and there's some flip around business with x and z. And here, 1, 2, 3, 1, 2, 3, 3. No, 1, 2, 3. Okay, so this one, 2, 3. No. 1, 2, 3. No. Okay, so this last one is tricky because there's not any dimension that appears to have stayed the same for all magnitudes. Oh boy. So this last one doesn't fit in with the way that we've been trying to do this, because I'm seeing here that there's nothing where there's no dimension where the column where x, y, or z where everything stays the same except for the sign as the first one. So something has been done here where I mean, you can also combine um, orientations in the 3 dimensions, but that'd be, I mean, that would produce more that. Man, this is tricky because I think that we can actually get, somewhat towards the solution if we can figure out just how to compute all these different orientations. But I am stumbling on this some. Because here, the coordinates have like fully rotated around. Ah, man. Scanners don't know their rotation or facing direction. Due to magnetic alignment, each scanner is rotated some integer number of 90-degree turns around all of the x, y, and z axes. Because if we're just counting like integer number of turns around x, y, and z axes, we can do 0, 1, 2, or 3 for each of those, then that would suggest 64 orientations, but that's obviously not right. There are 24 different orientations. I mean, there are 6 permutations that you could choose of x, y, and z. And then you could try, 4 rotations off of that. But which dimension would you choose to rotate about? If you were to do that is the question. I get a feeling that the reflection thing is wrong. But the question is, what's right? Well, I guess facing positive or negative x, y or z each of those are really obtained by rotations um, from the, I mean, if we say that, like facing positive x is, the first one, then, there would be rotations about the z or the y axes that would give those, so there's 6 facings that would also be obtained by rotations there. So yeah, so maybe oh boy. Um trying to Rubik's cube this thing, I guess. Um okay, so rotate 90. We will say about the z-axis, z rotation number of times. And then for each of those rotations, there are 4 ways to view what is up. And those will be rotations about, we will say, the x-axis, what we consider to be out x from that position. So then we will go through those signals. Rotate each of them. And these are going to be rotated around the x-axis because we're changing the way that we consider x to be pointing in the initial outer rotation. and those will be X rotation turns. And so then we will all orientations dot in place back that oriented version. And then we also want rotations about what we consider the y-axis to, tip it up and down in z. So we'll do something very similar to this, but for y rotation, we're only going to use 1 and 3 because those will get us the directions that are not covered in the other rotations that we did. So here we want to rotate about the y-axis that many times, and then we'll still do the x rotations. And maybe this sort of Rubik's Cube twisting here will get us the actual rotations that we want. Let's find out. Gosh, this is a tricky one, isn't it, though, folks? Let's see if we find everything from the examples. So, we have, the initial thing, nothing changed. Look for 1, -1, 1 somewhere. 2 - 2, 2. 3 - 3, 3. 2 - 1, 3. -5, 4. -6. -8, -7, 0. Okay. That's 1. Okay, let's look for 3 -1s in the first row. 3 -2s. 3 -3s. Okay, not that one. Nope, not that one. -1, -3, -2. 4, 6, 5, -7, 0, 8. Okay, that one's found. Let's look for 1, 1, -1. Okay. 2, 2, -2, 3, 3, -3. Okay, not that one. Bear with me as I check these manually. I know it's tedious, but 3, 3, -3, 1, 3, -2, -4, -6, 5, 7, 0, 8. Okay, and finally the last one. So you want 1, 1, 1, 2, 2, 2, 3, 3, 3 to start. Not that one. 3, 1, 2, -6, -4, -5, 0, 7, -8. Okay, I think we actually have the rotations right now. Okay, so the way, the reflection, complete red herring shouldn't have done reflection, but basically we are doing one series of rotations to figure out where positive x is pointing. So we can rotate around the z-axis 0, 1, 2, 3 times. And then it can also be pointing up in the z-axis and down in the z-axis. So that's those 1 and 3 rotations in the y-axis, get those. And then we go inside, and once we have oriented x, we rotate 0, 1, 2, or 3 times around the x-axis, and then that gets us all of our different orientations. Okay. That part of the problem done. Now that we've done that tricky geometry, we need to move on to other stuff. We need to actually try and assemble the map together. So given a pair of sensor datas, and we'll use 0 as the reference sensor data, I guess. We need to find another sensor that overlaps with 12 beacons. So for all of the possible orientations of that second sensor, we can, exploded. So basically, like we can say hmm. Well, what we want to do is for what if we find a match between two sensors for the second sensor, we want to orient it and we want to find its position. So basically, yeah, well, I'm gonna put an optional in here that is a point that is its point in 3D space, and not vec point that is its canonical position. And so initially that's going to be unset for everything except for the first sensor, but for the first sensor, that's going to be at the origin. So not first, front dot position equals grid 3 points k origin. Okay. So we'll have this match beacons function, and it is going to take a known sensor and a candidate sensor to match against. So we'll say so we'll say for for all the 24 orientations in that candidate that we're trying to match against, we can say for I mean, I guess we can do every possible pair of beacons from the two. So we'll yeah, I guess we'll say for in known dot beacon signals. we can say that we'll do a vector from one to the other, and we'll see if that offset makes sense for the other stuff in the candidate. Yeah. So we'll say const. So then we'll do another loop over the inner signals, and we'll say int matches equals 0, and then another loop we'll call this inner signal check. See, now I'm beginning to think that some of these might be better off as sets. Yeah. No, this might actually be okay. If inner signal check minus outer signal equals that offset, then plus plus matches. If matches is greater than or equal to 12, then we have an actual overlap here, and we will say that candidate orientation we're actually going to fill in here. We'll say candidate orientation dot position equals known dot position plus offset. That problem? Oh, yeah. Known dot. We'll dereference that to get the actual value. Oh, great. More can't infer template arguments for this. So what are the things that it doesn't like here? So we're gonna get to solve some C++ runs here. It doesn't like 300. It doesn't like 320. So 300 is a point plus a vector. 320 is a point plus a container of vector, but in either case it can't infer dimensions. So we'll just say we declared that up here, and it was fine. No, we didn't actually. We had plus equals, but we didn't have plus defined. Let's... Yeah, okay. So, I'm just missing some stuff here, but I'll just say point operator plus equals const vec and vec. Not plus equals, just plus const return, say, bingo. Okay, that's all we need to do, and we can, do something similar here for the minus. Fun with operator overloading. Okay. Otherwise, return null opt. Not null opt t, just null opt. We couldn't find a match. Okay, so what this loop is doing is in the outer, we're looking through all the different 24 orientations of this candidate that we're trying to match with regard to known. And then for each of those, for each pair of outer and inner signals, we're saying like, okay, if this pair is a match, we'll find the offset between the two, and then we will try and count up the other matches if that offset with that orientation works, and if we find 12 or more, then we have an overlap, and we know we have fully resolved this candidate into the canonical space, and we can move on from there. So what I'm now going to do is take another test input just from the website that has just 4 scanners as a report, and it tells us how some of these should match. So I'm going to go ahead and call this test2.txt. Yeah, that's something that we still had from, I don't know, maybe that was even from last year. But we'll go ahead and put that in there. And this one says that scanners 0 and 1 have an overlap, and that and it gives us what the position should be. So we'll say equals match beacons with sensor data 0 and sensor data 1. Sensor data 1, or sensor 1 resolved, should have a value. And then we will go ahead and print out the position of sensor data of sensor 1 resolved, and see if that is correct according to, and this is and an optional, so just say dot value. Okay. And let's see if this now works correctly. Just for that. Okay. So it didn't resolve between sensor data 0 and sensor data 1. So first thing I'm going to do is just... Hmm. Let's just have it spit out how many matches it thinks it's found after each of these. It's always 1. Well, actually, we don't know that for sure. If matches does not equal 1, I have it spit it out. If it's always 1, then, you know, something's off. Okay. It always thinks there's exactly 1 match. But those vectors are... Oh, you know what? We can't just compare it against the 1 outer signal. We have to loop over the outers and inners again. So I think. But let's see. Let's try that. Okay, so it says that relative scanner 1 must be at 6812. Okay. For some reason, those are all negative relative to... Oh, because we did inner signal minus outer signal. Let's flip these. Okay. So that is the correct offset according to number 1. So yeah, let's see here. We're going to have a set of resolved and a set of unresolved sensor data. And once we get everything in terms of... So initially, the only resolved one will be sensor 0. We'll do everything in the space of sensor 0. and then one by one we should be able to find um, some more sensors that match up with it, and then finally get everything resolved. So resolved will initially contain just that, and yeah, let's say it has that origin as its position, and sort of the main outer loop of the algorithm is, one by one we're going to resolve more sensors relative to the outside. So we'll say why now while and we'll pop the front of sensor data. Popping the front of a vector is not super efficient, but we're not I highly doubt. Oh, it only does pop back, huh? All right, we'll make it a what the heck? We'll make it a deck. I'm going to include the header for deck, not wanting to do autocomplete here. Okay. So we're just going to change sensor data here to a deck. Pretty much everything else should go the same. Pop front. Okay, cool. So while there's still something in sensor data, oh man, we're going to want to splice it out though, aren't we? Instead of just popping. See, now this makes me want to use a list, but yeah. Actually, I'm going to go back on just using a vector. We're going to just do horrible things with vectors, but it's whatever. So just go ahead and say erase the begin element there. And that erasing random elements from a vector is not particularly efficient. Maybe we would do a linked list if we were really worried about that, but there are not that many elements to do that. I doubt that that is going to be the dominating factor in this algorithm. So yeah, now let's get to actually writing that main loop. So say while sensor data is not empty, we will go through the unresolved sensor data. Although, actually, you know what? We're going to want to do this by iterator because of that erasing that I just said. So we'll just say for auto unresolved it equals sensor data dot begin. Unresolved it does not equal sensor data dot end plus plus unresolved it. Okay. So then for each of those unresolved, we will say if it will say auto is match beacons. Well, actually, we got to try this with all of the resolved ones. So we'll say for the known resolved stuff, if match beacons for that resolved one, and so if we found a match there, then we would say, well, we would put it in the resolved set. Oh, that's shadow. Yeah, we'll say resolve sensor. Don't want to shadow that name there. So we'll say we'll place that. We'll say matched is true. Other thing we're going to want to do here is say sensor data dot erase unresolved it. Get rid of that element there, and then if matched, we're going to break here. Oh, we should break up here too. So we'll break out of each of these for loops, and then just get it going again. And so, well, this will, well, I mean, this should get us to sensor data empty and have everything resolved. So let's just see if this actually runs, and then we'll try and get the information we want out of it. Okay, so it took a few seconds because it is kind of a brute forcey thing. Oh, and that was on the test input. Oh man, for our actual input, it might take too long. We might actually have to not brute force it. We will see. We'll see how we do here. But then to count everything up, I'll just use so flat hash set. We gotta actually include the header for that. And so we'll have a set of points for the beacons. And we know there's a lot of overlaps, but basically for each of our now resolved sensors, for each of those beacon signals, we can actually make a point, say beacons dot in place, and we'll get the position of that. We'll get sensor dot position dot value plus that signal. That will give us a point, and then we can read out beacons dot size, which is the total number of points. So doing it just on the test input, which should give us Oh, and we actually need to include the, we need to make sure that we specify that dependency in our build file. Okay. So now we'll try and run it. And on that test input that we're working with, it should say 79 beacons. It's taken a little bit of time. Okay, but it got the correct answer. Okay, so now it's a little slow on that, and I worry that it's going to be considerably slower on the other side, but, we'll see. I'm going to give it little progress messages. So you can kind of watch how it goes with the test input here, and then we will see how it goes with the other stuff. Okay. Yeah, and then once we get out of the loop, there's one more too. But let's go ahead and run it on our actual puzzle input. And it might take a real long time, because that is much bigger. I mean, it's going. How many sensors were there total? $37 or 38, depending on how you count. I mean, it's going. It's taking its sweet time. So while this brute force solution is going, we can maybe think about how to make this more efficient, hopefully. Oh boy. Maybe one thing is we can memoize all the different orientations. Yeah. Yeah, I like the idea of that. So we can just say, we got to make this mutable. And I'm going to make it private because it's not part of the public API of this. But, and we do return. Well, yeah, okay. We'll race with the brute force solution, see, how quickly we get there. But we could also probably parallelize this, but for now, we'll just use single-threaded tricks. So what we're doing here is trying to avoid the expensive cost of recomputing all the orientations for all of the signals all of the time. And these copy constructors are no longer working. But we can make that work. Although, looking at all the ways that we use sensor data here too, I just want to... I mean, this is not going to be in any way correct. I'm just seeing what else breaks with this. Okay. I'm going to make this shared pointer, which is bad. But what the hell? Oh, man. Now, why is this a problem? Oh, because, yeah, it needs to be shared pointer. This is not right. No. I mean, I do want to memoize it, but I need to do it in a way that is not going to I need to consider how sensor data is used, because it's used as a very value-like type right now, and I just need to make sure that we don't that's going to do reference lifetime extension. Okay. That we don't screw this up otherwise. So, okay, all orientations is really only called here. If we made that const, we can't assign it here, but okay. Okay. And our solver is crunching along here. It will get here eventually, but now I think we can, yeah, make a copy constructor where we copy just position and beacon signals. And now we can do our memoization trick, I think. I'm doing this as a vector, as a unique pointer, and not an optional, because this is going to recursively store pointers to sensor data within itself. So Default constructor should be fine there. Okay. I guess we just need to give it a default constructor. So if we've already pre-calculated it, we're going to return that. Otherwise, we are going to make that memoized vector. So we'll just remember all these rotations that we've calculated because, oh yeah, we're going to make this mutable as well. Well, actually, yeah, because this is a const method. And, you know, this doesn't actually, like, we're calling it mutable because this doesn't actually change the logical value of this thing. It's just used for memoization. So then, all orientations, blah, blah, blah. Okay. That should all work with memoization, and we're about halfway there on that. The problem is Basil is not going to want us to. I want to keep it running is the problem, but I don't know if Basil is going to like doing a second concurrent build. But, you know, just for the heck of it, I mean, we'll see if it likes this. Otherwise, it might just tell us to kick rocks because there's a build already running. And no, there is not. Although, it seems mad about something else. Copy assignment operator sensor. Oh. We need to write an assignment operator because now that we've actually started not defaulting this stuff. Well, you know what? Let's go ahead and write everything. We'll write a move constructor. We'll write a move assignment operator. Let's do everything here. If we're moving, we will absolutely steal that. Nothing due for self-assignment, otherwise, reset that because the underlying data reset. Yeah, actually we should move these others as well, even though they are copyable. It'd be more efficient if we can move them. And then we will also write a move assignment operator for sensor data as our very brute force solution slowly grinds along. And here, since we're moving from other, we can actually steal its all orientations if it actually does exist. Okay. So this is the one with memoization. Still kind of slow. As slow? I don't know. Yeah, it feels like maybe it's going a little faster, but it's hard to tell. Okay, so we memorize the different orientations of the sensors. Um, is there another way that we can make this faster? So it strikes me that in the main loop here, um, we are always. I think we are rechecking pairs of resolved and unresolved sensors um, a lot more than we need to, because you know if sensor 0 only matched against one thing from all the other unresolved sensors, it doesn't make sense to check everything against sensor 0 again. So I think maybe we want to do this in kind of let's maybe instead of just yeah. I think there's something to that. So instead of having just this resolved vector, um, I think um, we'll do like exhausted. I don't know. Eventually, everything will get into exhausted, I guess. Um, get a little more progress info here. Okay. So I'm going to flip the order of these and do 4 auto and resolved. Let's just say that should be const sensor data add. There we go. We will then go over the unresolved stuff in the inner loop. And we can see our other brute force super expensive solutions racing each other. But And actually, we're going to want to do this as an iterator as well. So we'll say auto resolved it equals resolved dot begin. Resolved it does not equal resolved dot end plus resolved it. Okay, we do that between, we try and match resolved to unresolved, and if maybe resolved dot has a value, then we have a hit here. So first things first is resolved dot in place back. We're going to put our newly resolved element there. We are going to erase it from the pending sensor data. Matched is true. You're going to break out of that inner loop. Now if we get down here and we haven't resolved anything, then well, so if matched, then we break. But otherwise, that resolved it is no longer valid, and we need to go on to the next. So what we will do is put it into the exhausted set. See how these are going. Erase it from the resolve set, and then we are going to break again because those iterators have become invalidated. So we just need to start that loop again, and that should be fine. We'll actually do resolve size plus exhausted dot size. It's going to give us something a little more accurate there. Okay. Yeah. Put that final one in there. And then we just need to go over both the resolved set and the exhausted set. Well, actually, we just can just put everything that was in the resolved set in the exhausted set. So we'll just say exhausted dot in place. Let's see here. Yeah. I think what we want is exhausted dot in place. Or actually, insert will work here, but yeah, exhausted dot insert, exhausted dot end, and we will make move iterators. Move iterators on the resolve set, resolve dot begin through resolve dot end. So this make move iterator is just going to convert it so that when we move stuff into place, it's going to move from the values held in resolved instead of copying. And then we will do this over exhausted. Okay, so this new algorithm, first try that I'm going to give it, I'm going to try with our test input instead of the whole puzzle, because I just want to make sure that we don't have any glaring bugs in our algorithm here. So we'll do test2.txt. Okay, that gets us to 79, which is the correct answer. Now, it's a good thing I have a lot of cores on this machine, because we're going to go ahead and start this running this thing that skips the exhausteds on the whole test input. You never know. Maybe we'll get there. Haven't exhausted anything yet, amazingly. I mean, the more we exhaust, the easier going it's going to be, but I don't know. Beginning to think about other ways that we could possibly optimize this algorithm. Although maybe our first attempt will finally get there before we can figure anything else out. There's got to be some other algorithmic insight that makes this even faster, because like generally, you know, even these really tricky problems, you get to a point where there is some kind of solution that will run in like 10 seconds or less if you just get everything algorithmically right. So obviously we do not have the fully optimized solution here. But we've got some things that are, you know, slowly but surely getting there. So we've got our memoized all orientations. Oh, you know what? Even with this exhausted optimization, I realize it's still kind of like an n-squared search. But we only need to find like all the possible pairs. Like it actually, yeah. I realize now that even with the exhausted thing, we are still rechecking a lot of possible pairs. So we can optimize this even further, I think. Let's see how we would do that. Well, so we've got this exhaustion mechanism. I think if we go through and try to fully exhaust each one in one go, that would be the way to do it. So, ooh boy. Oh, okay. First one finished, 547. Well, let's put that in the website while we're thinking about how to make this even faster. Or, you know, keeping it 100 with you to make it fast at all. But okay, 1 gold star. Part 2. Just to appreciate just how big the ocean is. Using Manhattan distance, how far apart do the scanners get? Okay. I mean, that's easy enough. We just got to go through all the pairs of scanners and compute their Manhattan distance, which we can definitely do. But, yeah. Well. let's go ahead and write that in here. And then we will say powder it over exhausted. Although I guess it doesn't even hurt to compare a sensor to itself, because its Manhattan distance from itself is just going to be 0. So that's fine. So we have already written the subtraction operator, although it is complaining about it because it's not in line. It's not in line. Well, we'll get in here. I mean, this is the thing that we want it to do. And you can't infer the parameter for some reason. Well, let's see if this works. More fun with C++ templates. Okay, so the second one has caught. So the final one with the exhausted mechanic is catching up pretty quickly, which is nice. But we can make it even faster, and we will work on that in just a moment. But first things first, I'm going to try and fix the subtraction between points here. Oh, I'm sorry, I haven't even been showing you the code. You can see that the version with exhausted has actually overtaken the version with just memoization already. So that's definitely speeding it up. But there's ways that we can make it even faster. But for now, I'm having a problem just with this Manhattan distance calculation because, I wrote this operator overload to subtract points from each other, but it is not working right now. So I'm going to mess around a little bit and see if I can get it working while that is running. If that op actually works, I will be very stoked. rid of that version. It just doesn't like something else. Oh, well, yeah, of course. Lovely. Yeah, so we got to the same answer quicker with that exhausted thing, and I think we can do even better than that. I think we can exhaust things quicker, basically. Let's do that on the test input. Oh, yeah, test2.txt, sorry. Take it just a little bit of time here. Okay, and it gives the correct answer on that, so I'm going to start this version running on our actual puzzle input. It is still going to be quite slow, but while that is running, we are going to try and make it faster. Because brute force is quite brute in this case. Okay. So I've got the sensor data. I'm going to change sensor data into a linked list. And the reason why I'm going to do that is because I'm going to want to delete multiple iterators in one go. So this iterators better be stable. Yeah. So we'll do standard list for sensor data. And what we're going to do here is we're going to keep a vector of the matches. We're not actually going to break out of that. We're going to keep on putting stuff on, and then we will have fully exhausted. So, we're going to erase all of those things that, everything that matched against, you know, a given thing. Then mean, this outer the way this outer loop works is inelegant, but I think that this will still effectively work the way that we want it to. So let's go ahead and try it on the test input. Okay, that's not actually working the way that we want. So let's see here. Loop through resolved. More printf debugging. Oh, okay, so this here we can break, I think. No, we still want to go through all the unresolved stuff. It's weird that okay, we did change resolved here, so we invalidated an iterator here. I'm wondering why that didn't trip us up before, but we'll say this is fine. Got to be very careful about iterator stability here, but I think that this is going to do it. This breaks no matter what, so we'll just say we'll make that a deck. Efficient access at the ends. Why the heck not? Now we will actually use a deck. Include deck. Okay. 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 So we'll get rid of this whole thing. We don't need that outer loop at all. That should be better. So we're just using this resolved as a queue for stuff to look at. Okay. So we got a problem there. A bad optional access. Oh, well, we've got an actual answer here. I'm going to go ahead and put it in. But I'm going to keep on going and trying to make, this solution better. Okay. We got it. We got the answers, folks, with our extreme brute force. And we were just over 1,000 on each of them. That's not the worst result, but oh man. So this, I think, is going to wind up being one of those kind of like legendary stumper puzzles. I think before I go on trying to optimize this, for sure spent a lot of time just kind of banging my head against the geometry and trying to do reflection to handle, which way does X face? Totally the wrong approach. The right approach was just to do like all the possible Rubik's Cube rotations. And so just combining all the rotations got us all the right orientations, and it got us there. And then we had a solution, but my gosh, it was slow brute force. And we had, this exhausted thing to optimize it a little bit, make it a bit faster, but still not at all great. So I'm actually going to keep on streaming a little bit more because I do want to see if we can make this new faster thing work. So the idea of this is that we find all the unresolved stuff that a given resolved Oh, that's why. Okay. Yeah. I can see why. I can already see why we failed. But the idea of this basically is that we're going to find everything in the unresolved sensors that matches a given resolved sensor. So we're going to completely exhaust it just in one path, so we don't waste a lot of time comparing things that we know don't have at least 12 matching beacons. So all that we need to do here is just say resolved dot in place back. That may be resolved, because that may be resolved contains the actual point offset information that we need, and it's not down here, just that removed here. So we rearrange that, and hopefully this goes nice and fast. Okay, went there relatively quick for the test. Let's take out the match line there, just so it doesn't get too spammy. Let's try it with the actual puzzle input now. Still taking a long time. I mean, I feel like this is faster. We're just ticking up the exhausteds, but what other ways can we make this fast? I mean, definitely some of the search can probably be parallelized, and there's probably some vector math that we could apply to, like do these comparisons faster, but those are techniques that aren't really in kind of the normal, like book of stuff you do with Advent of Code. Maybe match beacons can be made faster. So I'm looking at this here. We try all the orientations on the outside. We try every possible pair of inner and outer signal for the possible offset. And then we do all of the checks. I think we can optimize match beacons some. Because if we just calculate all of the offsets between outer and inner, if we find that, we can calculate the, okay, so I'm liking this now. Yeah. Yep. So we'll just keep a set of the offsets here. Then we go through outer and inner here, and we'll just put the difference inside that offsets map. Now, I won't quite delete all of that right now because I'm going to copy some of it, but basically all this stuff in here doesn't really matter because we'll get down here and we'll say if offsets.size is greater than or equal to 12, we've got enough overlap, then we do this whole thing. Oh, man. Nope. We need to do that a little bit different. We'll do a map to counts. And we'll need to include flat hash map as well here. And now we'll just say offset counts of outer signal minus inner signal. We'll just plus that. We'll increment that. And now we'll say just for and offset counts. If we find an offset that appears correct for more than 12, but for greater than or equal to 12, then we can do this. So yeah, that should make match beacons considerably faster, and we can just get rid of all the rest of this stuff. Okay. Let's run it again, see how fast that is. Oh, and we need to obviously include the dependency for it. Okay, it's going way faster now, as you can see. It's not, you know, mere milliseconds, but it gets us the correct answer in like a matter of seconds, as opposed to, waiting some minutes for it to finish. So, yeah, that was definitely an improvement. I think this is probably about as fast as I'm going to get it tonight, and the stream is approaching a record-breaking 3 hours, so I'm pretty happy with where we've got this now. This was a really challenging one, but I think a really fun one. I really enjoyed doing this with you tonight. Thank you for hanging out on the stream. If you're watching this on Twitch, remember, check the channel profile there. You'll find links to my YouTube channel with the stream replays and the GitHub repo where I upload all the code that we write. If, on the other hand, you're watching on YouTube, just go ahead and check the video description right down there. You're going to find links to the Twitch channel for the live streams, and once again to that GitHub repo for all of the code. Like I said, this was a challenging but fun one. Big challenge in the first place, just getting the different possible orientations right, and was definitely slowed down by messing about with reflections when I should have just done everything with rotations, and that turned out to be the correct way to do it. But checking against the samples that we gave us definitely helped head off those bugs to begin with. Then, we had a very brute force solution that took a long time, and we could, kind of start sanding the edges off it again. So we say, well, first, we're not going to try and rematch anything that already has, but that we already know doesn't have any more possible matches, and or say, okay, we're going to exhaust all the possible matches in one sweep. We're not going to compare two different sensors against each other twice. And then finally we're like, okay, for the match sensors, and also we can memoize all the different orientations for a sensor as well. And then finally for the match beacons, the realization that instead of calculating every possible delta between 2 points and then checking all the other points to see if they have the same delta, just doing those passes, computing all the deltas and just counting up the ones that are identical. And if there are 12 or more, we know that we have a match. And so finally, with all those optimization techniques, we got to something that is not completely heinous in terms of its runtime. In fact, let's go ahead and time it here, see how fast it actually goes. $12. Not bad at all. Could probably get it faster. I'm sure there are other optimizations to do, but I'm pretty happy with that. So thank you again for tuning in to this marathon stream. I hope that you enjoyed it. I definitely had fun with this puzzle. It was a big challenge, took a while, but I'm pretty satisfied with where we wound up. So thank you very much for watching. I hope to see you again tomorrow night. Bye-bye.